All right, nerds. Today we are learning all about a brand new coordinate system, polar coordinates. Up until now, the only things that you have ever graphed have been in x, y. You ever notice how those things are always making little squares all over the place? That's called the rectangular coordinate system. Polar coordinates are basically circular coordinates. This is what a polar coordinate grid looks like. Okay. And that's not all. There are others. There's there's three-dimensional systems as well. So like the three-dimensional version of this would be spherical coordinates. There's also conical coordinates that are shaped like a cone. And there's also cylindrical coordinates. Yes, what's up? You want to go back to your mother's classroom? Yes, you can go. Bye. Bye-bye. Okay, well, whatever. You guys must smell bad or something. Anywho, let's talk about what's going on in the polar coordinate system. First of all, like I said, it's circles, right? So what we're... hold on a second. All right. What? No, I had to call my wife and let her know that he was on the way. Dumber mouth, wow. A lower course than this one. She teaches geometry. Yes. Anyway, all right, so we were trying to do... so it's circular, right? What these coordinates do is they give us a radius and an angle, r comma theta. Instead of x comma y, it's r comma theta. Cool? Some basic vocabulary. The origin, O, is also known as the pole of the coordinate system. Now there's somebody at the door. We're not going to say the positive x-axis, but this one that points out to the right, this is called the polar axis. Okay? So it's from the origin and goes to the right. I already said polar coordinates are r comma theta, radius, and angle, where r is a directed distance. Anybody in physics? A couple of you are. What's another name for a directed distance? A vector. Yeah. So vectors are not assessed in AP Precalculus, but they are part of the Precalculus curriculum if we have time. In Precalc Honors, we learned vectors before polar coordinates because the knowledge of vectors makes these things easier to work with. We're gonna have to do it without vectors. Just realize that the radius has a direction, which means it could also have opposite directions. So you can now have a negative radius. Negative radius is a possibility in polar coordinates. And what a negative radius would mean is point the exact opposite direction of what the positive one would have pointed. Okay? And theta is the directed angle, and the reason why we say it's directed is because positive angles open counterclockwise, whereas negative angles open clockwise, which we already knew that to be true. Okay? So here is an example of a polar coordinate. This is 3 comma pi over 4. I find it very useful to also plot a coordinates reflection across the origin. So that would have been here. Now I could call this P prime or something like that if I wanted to. I'm not going to make you do that. It just means it's not point P. It's a reflection of point P, literally across the straight line. And the reason why I like to see this thing is because this shows me where all of the negative radius versions of this coordinate are. And the reason why I say it like that is because there are an infinite number of ways to write the coordinates of this specific point. And all of those infinite ways that have a positive radius, look at this dot. And all of the infinite ways that use a negative radius, look at this dot. Don't get this confused. This is the actual point in space. But if you wanted to give me a coordinate for it that has a negative radius, you would reference this point. For example, I could say positive, if this is a pi over 4, this is 5 pi over 4, correct? Another way of writing the coordinate 3 comma pi over 4 is negative 3 comma 5 pi over 4. Because this dot is 5 pi over 4 away from the polar axis, but the negative 3 radius says I'm looking the wrong direction and goes up there. Okay? And we could use negative 3 and negative 3 pi over 4. That just would have gone this way. And then, of course, anytime you add 2 pi or subtract 2 pi to either one of these things, you're still in the exact same place. Cool? So again, I find it very useful to plot a point and its reflection. That way I can write out several different ways of the exact same coordinate. And there's like 4 basic ways. There's positive radius, positive theta, positive radius, negative theta, negative radius, positive theta, negative radius, negative theta. So all the combinations of positive and negative. Make sense? Don't worry, we'll practice. All of these are polar coordinates. We are going to plot 2 comma pi over 4. The way that I like to plot polar coordinates is I actually look at the theta first. Because unlike x comma y, it really doesn't matter which one you look at first. I like to use theta first. That way I can decide where I should have been looking. So this is telling me look to pi over 4. Pi over 4 is halfway between 0 and pi over 2, so pi over 4 will be here. Here's pi over 4. So I look to pi over 4. I know I'm looking at the second ring. Do I get to stay at pi over 4, or do I need to reflect? I get to stay. And the reason why I get to stay at this angle is because this radius is positive. So this is a point at pi over 4 on the second ring. There is point P. It's easy when it's positive, positive. So you go to the second ring, go to this angle, and stay where you looked because you don't have to reflect away. But like I said, I do find it useful to put the reflection on here as well. I'm not going to write P prime, but just consider that red dot P prime. What I want to do is I want to write 3 more versions of this coordinate. Right now I have the positive, positive version. I'll even write them in blue and red. This one's blue. Here's another blue one. Blue means, as far as what I'm writing, positive radius. So I want to land here. So I'm referencing the blue dot because positive radius, but I want to use a negative angle. Negative what? 7 pi over 4. There you go. Negative 7 pi over 4. I should have left myself a little bit more space to write that. Negative 7 pi over 4. It's essentially this angle minus 2 pi. So that starts here at the second ring and goes whee, almost a negative full circle. Now let's write out 2 versions of negative radius. Negative radius means I'm trying to land here. Don't worry, I've already said the radius is negative, so no matter what, I'm going to reflect back up to here. So because that's all it is a reflection along a straight line. Let's go with the positive angle. What positive theta gets me to this red dot? There it is, 5 pi over 4. Bless you. 5 pi over 4. And the other way of writing this out would be with a negative angle, negative 3 pi over 4. So as long as you have your coordinate and its reflection on there, it shouldn't be too hard for you to find these 4 versions of the coordinate. And like I said, there's an infinite number of them because I can add or subtract 2 pi to every one of these thetas and I'm still at the same point. Okay? Making sense? What's happening? Again, if you're trying to write a coordinate using a positive radius, reference the actual coordinate. If you're trying to write the coordinates with a negative radius, reference the reflection. Cool? All right. Let's do, this one already has a negative radius. So I'm going to go out 1 ring. Then I'm going to go to pi over 3, which by the way is here. No, it's not. That's pi over 6. My apologies. That's pi over 3. There we go. 2 pi over 6. But anyway, it's pi over 3. So I go out 1 ring. I go to pi over 3. Do I get to stay there? Nope. Reflect. So it's actually there. There is point Q. But its reflection would have been here. So this would have been a red dot because it's negative radius. By the way, this whole like red-blue thing, that's just me. That's not like in a book or anything. Okay. Yeah. Why are they rings? Because angles open. Because it's a radius of a circle. No, it's a radius of a circle. See, all of these are small circles. So this is a circle of radius 1, radius 2, radius 3, all centered at the origin, which is the pole. So like if you wanted to graph the circle, if you wanted to graph a circle centered at the origin, the unit circle, its equation is literally r equals 1. That is the equation of the unit circle in polar coordinates. R equals 1. So let's write out the other versions of this coordinate. When we do these, I'm not going to bother doing extra versions because we kind of get it by now. But let's see it. Let's get the other red one since we're already doing it. So I don't know why I put a red dot when I'm going to write in red. Stupid. Anyway. So I'm going to reference this dot. I already know negative radius positive theta. Let's get negative radius negative theta. How far is that? Negative 5 pi over 3. Forgot the pi. Essentially, pi over 3 minus 2 pi. Now let's get the 2 first versions, like, in the first 2 pi of this one. So we know we're going to be dealing with positive radius. Let's get positive theta. How far do I have to go to get to there? 4 pi over 3. This is 3 pi over 3. So it's 4 pi over 3. Basically, how far apart are these two in radians? Pi. It's like tangent. They're pi away from each other. So use add pi or subtract pi, right? So add pi or go from 0 to there. Either way, you're going to get 4 pi over 3. And the other one with negative theta goes here. What is that? Negative 2 pi over 3. Yeah.
Why is the actual equation they gave us not one of the equations for blue?
Oh, okay, so I'm doing red for anything that had a negative radius. Because that's going to be the reflection. The actual, like where it lands in space, I'm putting in blue. So it lands here in space, it lands here in space. But this is the reflection of it. But the actual point where it is down here in quadrant 3. That's why. So I was just putting where it actually is as blue and where its image is, like its reflection. Yeah, where it actually is positive radius. That's how I've been doing it. Is that okay? That's why I didn't put a letter on the red one. I'm trying to show you this is the actual coordinate. These are just different ways of describing that one point in space. Because they're coterminal, I mean, you could just keep adding 2 pi all you want, So let's do these, and I'm not going to bother writing out different versions of them. Point R. It says go out to the third ring, 1, 2, 3, and then negative 30 degrees. Boop. Done. There it is. I went out to the third ring and went clockwise 30 degrees. Ta-da. There it is. And this one. It says go out to the second ring, then go negative 7 pi over 6. Here's negative 6 pi over 6. There's negative 7 pi over 6. Do I get to stay there? No. It's here. And here's why. Here's negative 7 pi over 6 radians. But the negative radius says, don't stay there, reflect away. This is where point S is. So I went out to the second ring and then followed negative 7 pi over 6. Radius was negative though, so I had to reflect away. Is that okay? You guys all right with that idea? How I did that? I always start with the theta. I mean, I look at the number to see which ring I'm on. Then I follow theta, and then I ask, do I stay or do I reflect? Should I stay or should I go? Yep. Guess what? You know all that stuff I just did with the whole image and stuff like that? Yeah, there's formulas for it. I don't know these formulas. Look how awful they are. It's freaking terrible, right? I don't know those formulas. I just know reflect away and spin positive circles and negative circles. Like, I don't know. So I don't do any trig without pictures. I mean, it makes sense. I could read it and I know what it says. But why bother committing it to memory? You know? When I know why it's true, I don't need to know the formula. That's just one more thing I'd have to memorize. Or two things, I guess. You know? Alrighty, so it actually wants us to get other versions of 2 comma 2 pi over 3. So let's go ahead and get them. Blue, because positive radius. I'm going to go out to the second ring, and then I'm going to go to 2 pi over 3. Which quadrant is that in? Quadrant 2. It's actually out here. Here is 2 pi over 3. It's this one. On the second ring, it's positive radius, so I get to stay there. Booyah. I guess we'll label it point P. It doesn't have a name. So there's point P. I'm going to draw its reflection on here as well. Its reflection's right there. It's on that spoke, just across the origin. Let us get the positive radius negative theta. So how far would I have to go negative angles? Boop. Boop. How far is that? Yeah, it's negative 4 pi over 3s. Literally this number minus 2 pi. Or you just count. How about the two negative radius versions of it? So when I do the negative radius, I'm referencing this red dot. So we know it's going to say negative 2 comma. They'll both say negative 2 comma. Positive angle. 5/3. Yep. So I drew this in second period. There's the 5 pi over 3. Of course, even easier would just be doing this. So what's the size of that negative angle? Yeah, negative pi over 3. Very simple. As long as you have the picture, it's simple. What do you guys think about polar coordinates and writing them in different forms? It's not too bad, right? It's not too bad. She says misleading. Why? As in, it feels simple. You know, the coordinates themselves really aren't bad. They're really not. It's really not bad. Okay. How about this? You know this point in space is a point in space regardless of what coordinate system I'm in, right? Okay. Well, we have a way of converting between angles and, or degrees and radians, right? Okay, well, guess what else we have a way of converting between? Polar and rectangular. You should be able to describe any point in space in either rectangular coordinates or polar coordinates. You should be able to move back and forth. The good news is it uses the trig stuff that we already know to be true. I don't have to teach you new trig, I just have to show you a way to use it. So that's the good news. The conversions are right here. We already know that because cosine theta is x over r, we know that x is r cosine theta. Because you just multiply both sides by r. Right? We've done that before. Where we wrote any coordinate we wanted in rectangle. Wait. No, we haven't done that before. Well, now you can. Now you can write any x comma y in trig form, also known as polar form. You just multiply both sides by r. And, well, sine of theta is y over r. So just multiply both sides by r, and you have y equals r sine theta. You already know that tangent of theta is y over x, and this is the equation of any circle centered at 0, 0. X squared plus y squared equals r squared. We've been doing x squared, y squared, and r squared, right? With our x, y, r. That's actually why the Pythagorean identity is true, because the unit circle has a radius of 1. So cosine squared theta plus sine squared theta equals 1, right? Okay. So here we have here we have polar coordinates, and we know they're polar because it says they are, and also because those are clearly angles. And we're going to convert them to rectangular. All right. X equals r cosine theta. This is r. This is theta. So x is 3 times the cosine of 5 pi over 6. Y is r sine theta, or 3 sine of 5 pi over 6. If you had your unit circle memorized, you would just multiply that unit circle coordinate by 3. I don't have my unit circle memorized, so I have to draw an image. Which quadrant is 5 pi over 6? Second quadrant. Okay. The reference angle is an over 6. So that's a 30-degree reference angle. There's always a 1 across from that. And this would be negative root 3. I wrote these two purple things up too high. So I'm going to have to get like diagonal with my equal signs. 3 times, let's look at cosine here. Negative root 3 over 2. And sine here, 3 times, 1/2. This polar coordinate is this rectangular coordinate. Negative 3 root 3 over 2, comma, 3 over 2. Those are the exact same point in space. It just uses the trig that we already know. Ta-da! Not bad, right? All right. Let's do it again. Tell you what, I'm going to draw the triangle this time first. That way I know how far up and down I can write. I'm going to draw a triangle at negative 7 pi over 6. What quadrant is negative 7 pi over 6 in? 2. Oh, It's this. This is negative 7 pi over 6 radians. It's coterminal at least to 5 pi over 6. So it's the same triangle. Cute, right? It's an over 6, so it's 30 degrees. 1, negative root 3, 2. X is r cosine theta, which is 2 cosine of negative 7 pi over 6. So 2 times, and we said cosine here is negative root 3 over 2. Oh, the 2's are going to cancel. And y is r sine theta, 2 sine of negative 7 pi over 6, which is 2 times 1/2. The 2's are going to cancel. This point in space is negative root 3 comma 1. Ta-da! Oh. How about that? Does anybody see it? What just got my attention? Those are the side lengths. It's literally negative root 3 comma 1. Because the radius was 2. If the radius had been anything else, that wouldn't have happened. But because the radius was 2, it ended up giving us the exact xy of the triangle that we drew. I didn't catch that in second period, and nobody said anything. Yes?
If the radius is like 2 square root of 2, would it be 1?
If it's... Wait.
Yeah, like 45.
So if I tell you that the radius is root 2, and the x and y are the same number... no, I don't want to say this. If the radius is root 2, then yeah, it'll be like 1, 1. But you'd have to be told that the angle is 45 degrees. You know what I mean? Speaking of, these are rectangular coordinates. We are going to find their polar equivalent. Okay? Now we could, and you know what? I'm just going to draw it. I don't like to do trig without pictures. I'm not trying to use formulas. Let me just draw the coordinate 1 comma negative 1. What quadrant is that in? Quadrant 4. Because this is just regular rectangular space. Oh. What's the radius on this? And the size of my reference angle is clearly 45 degrees, right? But it's in quadrant 4. So in polar coordinates, r is root 2. What do you want theta to be? Negative pi over 4. That one's really simple to use. Now, if we've been told that it had to be a positive angle, yeah, it would have gone this way and you'd have said 7 pi over 4. Now, what if it hadn't been a pretty one? What? Oh my goodness, again? Anyway, what do we do if it wasn't a pretty one, right? Like we knew just because of the coordinates that it was a pretty angle. So I'm gonna add an example. It's not in the paper notes anywhere. You could try to squeeze it in somewhere if you want to. Like, I don't know, there's some space up here if you wanted to do that. Or it's blank all the way on the back. I don't know what you want to do. But I am going to include another example. What if I told you the rectangular coordinates were 1 comma negative, no. Let me do something different. Negative 1 comma negative 2. And let's say I wanted that in polar coordinates. What quadrant is that in? Third quadrant. because they're both negative. How are you going to find the radius? Pythagorean theorem. Okay, 1 squared plus 2 squared is 5. Square root of that is root 5. So we know that our radius is root 5. That part's the easy part. Tell me, how do I find theta? Because it's not one of the special triangles. Other equation and go background? Is that what you said?
Yeah.
What are you trying to say? He says use trig. What do you mean? How? What did you say? You could use sine of theta equals y over r if you want to. And then you would have to use inverse trig to get the angle alone, right? Okay, let's see. Jack, you said sine. Is there anything wrong with using sine? No. But you know what you want to use almost exclusively? Tangent. But why tangent? Because you don't have to use it with the radius. That's why. Because tangent uses x and y. And every rectangular coordinate has an x and a y. And also because there's a good chance you're going to have to deal with a radical in your hypotenuse, right? And it's just a pain in the butt to type. So let's use tangent. So there's nothing wrong with using sine. There's nothing wrong with using cosine. It's just that it requires you to find the radius first. What if I just wanted to know the angle, right? It's called a direction angle. What if I just wanted the direction angle and I don't give a crap about the radius? Then you would use tangent, so you might as well just always use tangent. So let's see. Tangent of theta is y over x. So how do I get theta alone? Inverse tangent. Theta is tangent inverse of 2. And you guys want to do radians or degrees? I don't really care. Degrees? Okay. Good. My calculator's in degree mode anyway. Tangent inverse of 2 is 63 point, let's go, it's AP, right? So 3 decimals. 63.435 degrees. Somebody tell me why I don't like that. Where is this? It's in quadrant 1. Tangent inverse can only ever give you back results in quadrant 1 or negative 1. Same for sine inverse. Cosine inverse can only give us answers here and here. So are we screwed? Of course not. That angle that it just gave me is right here. So what do I need to do? What do you, no, negative 63 and change puts me here. How often does tangent repeat itself? Every pi or every 180. So just add 180 degrees to it. Or subtract 180 degrees from it. Doesn't matter. So if we add that to 180, that'll put us here. And that'll give us our polar coordinate of r. And then our theta would be 180 plus 63 and change, so 243.435 degrees. Or you could have been really slick and actually used this angle and then just said the radius was negative. Because look, so if you wanted to use that angle that's in quadrant 1, fine. Just use negative radius so it reflects. But that trick only works if you were trying to go from quadrant 1 to quadrant 3, right? Like if I had drawn it up here, you wouldn't have had a choice. You wouldn't have used negative radius. You would have used positive radius. but tangent inverse would not have given you this answer. Tangent inverse still would have given you this answer. Like if I had said this was -1 comma +2, that triangle would have been up here. So what would we have done? We would have said it's 63 and change before 180. So we would have subtracted it from 180. So it's the same work that you would have done when you were doing the inverse trig stuff. You just need to be comfortable reflecting your triangles around. Cool beans? All right, this one is actually kind of boring. This is the rectangular coordinate 2, 0. So what's the radius? 2. And what's the angle? 0. This point, any point on the positive x-axis, its coordinates are identical in polar coordinates as they are in rectangular coordinates. Isn't that fun? Anything? No, I said anything on the positive x-axis, which is also true for the polar axis. So any coordinate on the positive x-axis in rectangular has identical polar coordinates, or you could say any point on the polar axis has identical xy coordinates. It's kind of boring, actually. You know what's not boring? By the way, here's the formulas for the crap that we just did. I don't know those. Anyway, what's not boring is converting between polar and rectangular equations. Isn't that cool? This is a rectangular equation. It's in terms of x and y. And just like we can convert xy coordinates to r thetas, we can convert xy equations, I'm not even saying functions, equations to r theta. This will be the last one we do today. All you have to know, though, is all polar equations say r equals. All polar equations isolate r. Just like all xy functions are y equals, all r theta equations are r equals. So it's kind of backwards, but it is what it is. It's r equals. That's just how they did it. And we get to use, again, the same substitutions that we already know to be true. What is the trig form of y? What does y equal? R sine theta. And cosine is, x is r cosine theta. So we're going to substitute in this for y and this for x. It gives me r sine theta equals 1/2 r cosine theta quantity squared. There. We are trying to get r by itself. And just so you know, r can't be 0. Because if you have a radius of 0, yeah, you're at the pole in polar coordinates. So we're not even going to say r is 0. We're just going to say, well, let's assume r isn't 0. And if we're going to say that r can't be 0, you know what we're allowed to do? It's something you wouldn't be allowed to do if r was 0. You're allowed to divide by it. So since we're saying r can't be 0, we're going to divide both sides by r. And we can get r alone now. Multiply both sides by 2. Divide both sides by cosine squared theta. That gets me r equals 2 sine theta over, you know what? Instead of saying cosine squared, I'm going to say cosine theta times cosine theta. But why would I have done that? What is this? Tangent theta. And, you know, there's a 1 up here. What is this?
Oh, or
Secant theta. And there it is. 2 tangent theta secant theta in polar coordinates is this parabola. Isn't that neat? It's so friggin' cool. God, I'm a nerd.